Hello, and this time we're going to be doing an example of the use of the small signal approximation to analyze a circuit. This is the circuit, and we're told that the current flowing through this resistor and diode combination is currently 761.4 microamps, the voltage across the diode 338.6 millivolts. We're told the dynamic resistance of the diode, and we're asked what happens if the voltage source is reduced to 1.0 volts. Well, we've got all the details we need here to determine our operating point. That operating point is behaving like the sort of zero of our nonlinear circuit. And as long as we just consider the differences in currents and the difference in voltages away from our operating point, then we can use linear circuit analysis just by replacing all of the nonlinear components by their dynamic resistances. So here we have a voltage source there, and we want to know what happens when the voltage source in the circuit is reduced to 1 volt. So the change in the voltage is minus 100 millivolts. So I would have this as a minus 100 millivolt. That's delta V. That's the difference in the voltage here from my operating point. The dynamic impedance of a 1K resistor is just 1K. Because, as we've seen, for a resistor, its dynamic resistance is equal to its static resistance, is equal to just its resistance. That goes through this ammeter here, and then through a diode. Now, the diode has a dynamic resistance of 35.4 ohms. So, for small changes in current and voltage around the operating point, we can consider that the diode is just going to work like a 35.4 ohm resistor. And I'm measuring the voltage across that diode. Right. Well, this is quite a simple circuit to solve. It's just a potential divider. The current flowing through this circuit is the voltage divided by the total resistance in the circuit. So the current flowing through in this direction is going to be the voltage here, which is minus 100, I'll call it delta I, the change in the current registered by this ammeter here, will be the voltage minus 100 millivolts divided by the total resistance here, which is 1035.4 ohms. And that is equal to minus 96.6 microamps. Near enough. So that's the change in current flowing through. The change in voltage across this resistor, well, this circuit is a potential divider. If we consider the minus 100 millivolts here as being the input to the potential divider, the output to the potential divider is just the voltage across this resistor. So delta V, the change in the voltmeter reading, is going to be minus 100 millivolts times the resistance of this resistor, divided by the sum of this resistance and this resistor, which is again 135.4 ohms. It's just the potential divider equation again. That gives me my delta V as minus 3.4 millivolts. These are the changes in the current and the voltage away from the operating point. At the operating point, the current was 761.4 microamps, so my new current is going to be 761.4 minus 96.6 microamps, which is $664.8 microamps. And the voltage at the output is going to be the operating point voltage, which is 338.6 millivolts, plus the change. But the change is minus 3.4, so that's minus 3.4 millivolts. And that's going to give me 335.2 millivolts. So these would be my estimates of the new current and the new voltage across that diode. Does it work? Well, once again, we can try it in the simulator. Here I've built the circuit in the simulator, and I will reduce the voltage here from 1.1 volts to 1 volt. That's the change in voltage of minus 100 millivolts. Spot on accurate. This analysis was only an approximation. It was an approximation based on the fact that the dynamic resistance of this diode didn't change significantly over the change in current flowing through it. But as you can see, it's extremely accurate approximation to 4 significant figures in this case. It's a very common and a very useful technique. And that brings us to the end of this series of talks about linearity and superposition.